Hello, my lovely students. Welcome back. I have two word problems to show you application questions, but they both have two parts because that's what I saw the homework doing when I looked on Alex. So this first one, this is something Alex did all the time, but they asked you to find the interest rate given two of the numbers. And then once you have the interest rate, then they ask you to figure out something else. And it might be how long it takes the money to double or triple or quadruple, or how long does it take the money to get to X number. But the way you solve those, they all follow the same format. And the two problems are nearly identical as far as the math you do. So, all right. So we do have here continuous compounding, which means we have A equals PERT, PE to the RT. So we just need to assign what all of these are. So I know my A is my actual amount at the end. I think it might actually stand for like annuitized or something, but I don't know. Those are banking terms. I'm a math person, not a banker. All right, and then P for principal is our initial investment amount, which here is the 2,500. And then E is a constant, and then R and T. So R is what they asked for. So that's our unknown. And then they told us we get to this amount in 10 years. So when I plug 10 in for T, I'm going to get that number for A. So knowing that, I can back solve and find the R. So we're going to fill these into our equation. So we start with 3729.56. That's like a horrible 9. A little better. Then our P of 2,500. E to the, don't know what R is, but I know T is 10. All right. So first step here is, I want to get at the R. So eventually I'm going to have to get rid of that 10. But before the 10, I have to get rid of the E. Before I can even deal with the E, I got to get rid of the 2,500. So 2,500 is attached by multiplication. So we are going to get rid of it using the inverse operation of division to both sides of the equation. All right, now this crunches up to, I'm sure, some ugly number. Actually, it probably isn't that bad because 2,500 is like a factor of like 10,000. Let's crunch it up because I think this one will actually work out nicely. 3,729. Most of the time, though, I would just leave it. I mean, it is actually terminal, but it's a little ugly. All right, I'm still going to write it all, though. 1.491824. See, to my way of thinking, anything more than 4 decimal places is ugly. Now, R times 10 is the same as 10R. I left a little space there on purpose because the next thing we need to do is undo the E, which at the same time is going to bring our exponential down. Now, if it was any other base, you just log or natural log, but because it's E, use the natural log because that will actually completely undo the E and it's one less step we have to calculate. On the next one, we just got to use regular log or natural log because it's not going to be base E. So I can take the natural log of that and it's some disgusting irrational number. So I'm not going to crunch that right now. But I do have that as one of my steps, or one of my calculations to be done. And then over here, we have 10 times R now. That would come down on the line. And then the natural log of E, E to what power is E? 1. So we don't even have to write it, it's times 1. All right, so last step is get rid of the 10 by dividing by it. So we're going to take the natural log of that ugly answer, hit equals, then divide by 10. I do it that way because I'm used to old calculators. So let's do this. And let's put natural up. Not what I wanted. That is what I wanted. And then divided by 10. Wait, no. Equals divided by 10. 0.039999999532. So actually 5 nines. It does say up here to the nearest whole percent. Well, this is a decimal right now. It's not even a percent. So let's convert it to a percent first, which is move 2 decimal places or really multiply by 100. This is going to give us 3.99999 blah, blah, blah percent. But it said in the directions, round to the nearest whole percent. Now it's important to go looking for this because what they want us to round it to is going to determine the answer to the second part. Now, certainly there's a lot of arguments about degree of precision you could make here from a scientific perspective, but mathematicians don't pay attention to that. So this would round to 4%. So that is what we are going to use for our 4%. So now my equation, my A equals PE to the RT, because now I can solve for different A's, but my P would stay the same. I'm not changing how much I'm starting out at, but I know my rate now is 4%. So I can write 0.04 with a T. So this is now a new function. I want to know in 10 years, what's it going to be? Well, I know what it's going to be. That was actually what we just calculated. But in 5 years, I want to know what it's going to be. 50 years. You can put in whatever time number you want. If I want to know when is it going to get to 10,000, I can plug 10,000 in for A and back solve. And the back solve is going to look just like what we did here. So I'm going to take this and make a copy. And we're going to move it over here. We're going to move it somewhere. All right. So there's our equation. And then it asks about doubling. Now here's the fun thing about doubling. To figure out the doubling rate, you don't actually need to know the amount you're investing. All you need is the interest rate. The amount of time it takes $1 to double at this interest rate is the same as what it would take for $2,500 or $10,000. The amount doesn't matter because watch this. So we're looking at doubling. So if we started with 2,500, then our double amount is 2 times 2,500. Now I know that's 5,000, but I'm actually leaving it like that on purpose. So watch what happens when I put that in. So we are going to start with the same step, divide by the 2,500. And the 2,500s cancel out, and we're left with a 2. So if it was 5,000, I would have had 2 times 5,000, and 5,000s would have canceled out, and it would have been a 2. If I had 10,000, then 2 times 10,000, and it would have been a 2. If we were looking at how long does it take to triple, I'd see a 3 here after I divided. So if you get a question where it just says, how long does it take the money to double in an account with X interest rate? You don't actually need to know the amount. You can do some workarounds. So now we have just the number 2 equals e to the 0.04t. Now, just like before, I need to natural log both sides. So the natural log of 2 shows up so often in these problems because mathematicians just love, how long does it take to double? Or if we're talking about half-life, You'll often see the 2 in the place of the E in the equations, which is what we're going to see in a second. So now again, the exponent comes down to the line using that log property. So we have 0.04t, and then natural log of e would be 1, so we don't even have to write times 1. And then last, just divide out that 0.04. And now we are going to get a t number. T. All right, so let's clear this. So natural log of 2 divided by 0.04. So I have 17.3286, blah, blah, blah. Now think back, what is time in these questions? If we look, it was years. So this is not a money number, this is a year number. Usually with years, like when in doubt, you can go with 2 decimal places, but we're not going to make you choose between the two. So you're not going to see 17 and 17.3 to choose from. That's a dick move. But for time, I kind of stick more with one place just so it doesn't look like money. But we could even just, like, the answer could also be written, during the 17th year, the money will double. And sometimes online, Alex will ask it that way, where you're just filling in the whole number. Now, even if it was 17.8, we would still say during the 17th year, even though the number would round up, it's occurring between the start of the 17th year and the start of the 18th year. So just kind of think about your answer, think about what it means in the context of the problem, and different ways you could say that answer to have some meaning. All right. So there's that one. Now, down here, we have a second one I dug up from the book, and I was so lazy I didn't even type it back out. I just copied it straight from the digital copy of the book. So what we have here is they're dealing with a radioactive form of iodine, which has a half-life of approximately 8 days. But once it's inside the person, it actually has a half-life of 4.2 days. This is shorter due to it being, so some of it's lost to decay, but it's also goes out in urine, sweat, and saliva. So we're going to be focusing on that 4.2 days now. So when we talk about radiation dosages, they're in curies. In this case, it's millicuries because the amount is tiny. So with 100 millicuries of iodine-131 to start with, the radioactive level R, again measured in millicuries, after T days is given by this equation, this function. R equals 100 times 2 to the negative T over 4.2. So I want you to think for a second. So 4.2 is the half-life. So if I plugged 4.2 in for T, I would get 100 times 2 to the negative 4.2 over 4.2. Well, negative 4.2 over positive 4.2 is negative 1. 2 to the negative 1 is 1/2. So we end up with 50 millicuries left after 4.2 days, which is what we're supposed to see. That's what a half-life means. This is the amount of time for the radioactive isotope, for half of it to be gone. And technically, you can infinitely divide by halves, so theoretically, there's always some there. But really what you talk about is when does it get to a safe level? So down here, A is asking, state law mandates that the patient stay in an isolated hospital room for 2 days after treatment with iodine-131. Determine the radioactivity level at the end of 2 days. Run to the nearest whole unit. All right. So we're going to use that same function, but it's telling us at the end of 2 days. That means we're going to plug 2 days into that. because mathematicians are quite literal. So we can even kind of think of this as function notation if you wanted to say like r of 2, but that's not r times 2. And so some of you guys get a little tripped up by function notation. I'm not going to do it here. So we have the 100 times the 2, and then negative, put the number in for t, and divide it by 4.2. So using a different color, the number we are substituting in is that 2. And now everything on the right side is a number. We can crunch all this on the calculator in one go. And that is going to give us the radioactivity level. Remember, radioactivity is measured in millicuries, named after Madame Curie. Okay. Whew. All right, to the, where is it? Never remember where the negative ends up. There it is, -2 divided by 4.2. Close. Times 100. So after we multiply by 100, we have 71.887, blah, blah, blah. So 71.88 round is going to be 72. So there are 72 millicuries approximately after 2 days, which also makes sense. Remember, 4.2 days was the half-life, so the amount we see now should be greater than half. Now here I recopied that last sentence from the original problem so we can calculate and do the other half of the problem. So after the patient is released from the hospital, the patient is directed to avoid direct human contact until the radioactivity level drops below 30 millicuries. For how many days after leaving the hospital will the patient need to stay in isolation round to the nearest 10th of a day? Okay, anytime you see a word that gets italicized in a math problem, it should have like a giant flashing sign pointing at it. So for how many days after leaving the hospital? So not how many days from getting the treatment, but we're going to take those 2 days from the previous problem once we get our answer and subtract them off. So this is like annoying because on a multiple choice test, both answers will be present. All right, so we have our, let's not use a highlighter. So we have R equals 100 times the 2, negative t over 4.2. And this is, we want it to get below 30 millicuries. So that is the radiation level. And I want this thing to be less than that 30. So we could write it as an inequality and solve. Generally though, we would do all the same steps, except potentially for that negative towards the end. Or we can just set it up as an equation, because we do have like a common sense way to figure out which way we would go after that. And they told us to round to the nearest 10th of a day. That is a time number, so we are solving for t. So first step is get rid of the 100. Start at the outermost last operation and work our way in. So this becomes 0.3, 3/10. Now we have the 2 to the negative t over 4.2. So I need this t to come on the line. Now before I was using natural log because we had base e and natural log is on the calculator. So log base 2 would bring the exponent down and get rid of the 2, but I can't easily type log base 2 on the calculator. So I'm just going to use regular log base 10 because we have that. So that is our next step, is to apply a regular log to both sides, and it has to be the entire side. So you can't like term by term. If there's a sum or something, it's the log of the whole thing. So the log of 0.3 is something I can crunch on the calculator. And now this power is going to come down. So this is negative t. I'm going to write it as a more normal looking fraction now that it's not stuck up in the exponent. And so this is what we have for the moment. So I have the log of 3/10 on one side is equal to negative t over 4.2 times the log of 2. So a bunch of things going on here. First thing I would do is I hate fractions. I want to get rid of that fraction. I don't want to see 4.2 on the bottom. So I'm going to multiply both sides of the equation by 4.2. And over here on the left, it actually looks pretty nice. Over here on the right, just that part would cancel, and it is still right now negative t times the log of 2. And over here, 4.2 log of 3/10. So now this negative in front of the t we could think of as a negative 1. So that is being multiplied. So I can divide by negative 1 to get rid of that. And the log is also attached by multiplication, so I'm going to divide to get rid of that. So on both sides, I'm going to divide by, and you can just write or type on the calculator negative log of 2. Sometimes I prefer to see the number. But mathematically, it doesn't matter. They're equivalent. You can write the 1 or not. If it was any other number, though, you better write it because that will make a difference in the answer. The negative sign will make a difference here, but the 1 isn't going to change anything, just the fact that it's a negative. And then everything is gone from next to the t, so we now have just t by itself, and we are going to crunch that crazy mess. Now, whenever you have a complicated fraction like this, if your calculator puts the fraction bar and you see the top on top and the bottom on the bottom, then you can just type the stuff where it goes. But if you have an older calculator, like what's on the phone, you need to put the top in its own set of parentheses and the bottom in its own set of parentheses to ensure that the top gets multiplied together. If you forget on the top, it'll actually work out, but it's on the bottom. If you don't put this set of parentheses, then you'll end up multiplying by the log of 2 instead of dividing by it. All right, so let's go ahead and crunch that craziness. All right, so open 4.2 times the log of 0.3. And when I type log, it opens a parenthesis, so I had to close that one and close the one after. So it actually looks like what I wrote because I have the red parenthesis and the green parenthesis, and I've got 2 parentheses here. Let me see if it'll show up. Yeah. All right, now divided by, and we open it again, negative 1 times the log of 2. Close it, close it. All right. And you can actually kind of see on my phone, it pre-shows the decimal, but if I hit equals, then it actually crunches it up there and looks like we are looking at 7.29 blah, blah, blah. Yeah. And I stopped there because I was remembering it said 10th of a day. I was thinking years for a second. Normally half-lives are huge. So this is 7.3 days. She needs to stay isolated for a little over, well, but remember, they said after. Made the big deal about after, and I almost forgot. That's why sometimes, like, just highlighting it isn't enough. I might, like, put a big star on my paper to be like, remember, you need to take off too. So after leaving the hospital, well, she already spent 2 days in the hospital. So we minus 2 days. And she has to stay isolated for 5.3 days. So the hospital would probably tell her to stay isolated for 6 days just to be on the safe side. Or maybe 5.5, but you give a little extra to give people a room for error, because a lot of people don't like to fully listen to directions. All right. So that is one way half-life works and what half-life is even talking about. Math textbooks really love doing carbon dating questions because we know the half-life of it, and the question crops up a lot. Like I even did it in my general chemistry class. So, and I think you could probably also do it in geology. So FYI, just using this type of formula and back solving to figure out like what the time would be is useful. All right, so just 2 little word problems, just as an extra bonus if you wanted to see somebody else do it. You guys got this on the test. So take a breath, breathe, carry on.